In this worksheet, we're going to determine the convergence or divergence of certain infinite series. We're only going to look at series that are either geometric, telescoping, or series that can be shown to be divergent by the test for divergence. Example 1, determine whether the series is convergent or divergent. If it converges, find its sum. Part A, the sum n equals 1 to infinity of 5 times the quantity negative 2/3 to the n minus 1. Notice that this infinite series has a first term of 5 when we plug in 1 for n. Then each subsequent term is found by multiplying by negative 2/3 to some power. So we have a geometric series. Recall that a geometric series is a series of this form here. Every time we have a geometric series, we want to rewrite it in the form a, the first term, times r to the n minus 1, where r is the common ratio. Now, if the absolute value of r is less than 1, then the series is convergent, and the sum can be found by taking the first term divided by 1 minus the common ratio. If the absolute value of r is greater than or equal to 1, then the geometric series is divergent. So part A is a geometric series that's already in this form. A is equal to 5. R is equal to negative 2/3. And since absolute R is less than 1, this geometric series is convergent. So that means we can find the sum by taking our first term A over 1 minus the common ratio. Part B, the sum n equals 1 to infinity of 3 to the n over 8 to the n plus 1. So here we might suspect that this is a geometric series, but we're going to need to rewrite it in this format. So using properties of exponents, we can rewrite this series this way. Remember, when we multiply same bases, we add the exponents. So if you were to add the exponents here, you would get 3 to the n power. And if you were to add the exponents here, you would get 8 to the n plus 1 power. Now we can rewrite this as 3 over 64 times 3 over 8 to the n minus 1 power. And now we're in the proper format for a geometric series where A equals 3 over 64 and R equals 3 over 8. The absolute value of R is less than 1, so this geometric series is convergent. We can find the sum by taking the first term, A, over 1 minus the common ratio. If we multiply top and bottom by 64, we end up with 3 on top over 64 minus 24, which gives us 3 over 40. Part C, the sum n equals 1 to infinity of 2 times 6 to the n times 5 to the 1 minus n. Notice that we only have multiplication here. So once again, we're going to try to rewrite this as a geometric series, A times R to the n minus 1. We can rewrite 5 to the 1 minus n as 5 to the first power times 5 to the negative n power. Again, remembering that we would add the exponents on these two factors to get us back to here. Simplifying this a bit, we can multiply the 5 and the 2 to get a 10. We have a 6 to the n power. Then in the denominator, we have a 5 to the n power. Again, we want to have an n minus 1 power, so we're going to rewrite it this way. So just like that, we've rewritten our series as a times r to the n minus 1 power. So the series is geometric. A is equal to 30. R is equal to 6 over 5. Notice that absolute R is greater than or equal to 1. Therefore, this geometric series is divergent. Part D, the sum n equals 1 to infinity of 1 over 5 plus 2 to the negative n power. This series is not geometric because we cannot write it in the form a times r to the n minus 1 power. So we're going to have to try something else. With many of the series that we encounter, we're going to want to try a quick test for divergence at the very beginning. Recall, if you take the limit as n approaches infinity of the terms of your series, and that limit either does not exist or equals 0, then the series is divergent. We're going to be using tests for divergence quite a bit in this chapter, so it's a good one to remember. So we're going to take the limit as n approaches infinity of 1 over 5 plus. We can rewrite that 2 to the negative n as 1 over 2 to the n. If we let n go to infinity, this fraction will go to 0 and we get 1/5. Since this limit does not equal 0, we say that the series is divergent by the test for divergence. Part E, the sum n equals 1 to infinity of the quantity 1 over n to the 3 halves minus 1 over n plus 1 to the 3 halves. Here you could do a quick test for divergence in your head. Take the limit of each of these fractions as n goes to infinity and we'll get 0. So the test for divergence is inconclusive. Also, we're not going to be able to rewrite this as a geometric series. So we're going to have to try something else. Let's go ahead and look at the nth partial sum. Basically what that means is we're going to plug in 1, then 2, then 3, and see what these terms are all the way up to the nth term. That's going to look something like this. Now this pattern continues all the way until we get to the nth term. This is the nth term. This is the preceding term, which is the a sub n minus 1 term. The thing to notice here is that we have a bunch of terms that are going to cancel. That is, this negative 1 over 2 to the 3 halves cancels with this positive 1 over 2 to the 3 halves. And this negative 1 over 3 to the 3 halves cancels with this positive 1 over 3 to the 3 halves. This continues this way with all the terms going in this direction, including this one and these two. So our nth partial sum ends up just collapsing into the first term minus the last term. This is called a telescoping series, where you have all these middle terms canceling out. Now, by definition of an infinite series, it is said to converge if the limit of the partial sums as n goes to infinity converges. That is, our original series is going to equal the limit as n approaches infinity of our nth partial sum. This limit is equal to 1 minus 0 or 1. That is the sum of this series. Example 2, express each number as a ratio of integers. So the whole point in this example is to rewrite your repeating decimal as a geometric series. In part A, we have 0.2 repeating. That is 2/10 plus 2/100 plus 2/1000, and that continues on like that. In other words, we have 2 over 10 to the first plus 2 over 10 squared, etc. That's going to equal the geometric series n equals 1 to infinity. The first term is 2 over 10, and then each time we're going to multiply by 1 over 10. So we end up with something like this. Now go ahead and pause the video, plug in 1 in here, we should get our first term. If we plug in 2 for n, we should get our second term. And if we plug in 3, we'll get our third term, and so on and so forth. So this is geometric with a equaling 2 over 10 and r equaling 1 over 10. Notice that absolute r, which is 1/10, is less than 1, so therefore it's a convergent geometric series. And we can write the sum by taking a, which is 2 over 10, our first term, over 1 minus the common ratio. So we have 2 over 10 over 9 over 10. And this becomes 2 over 9. In part B, we're going to repeat this same process. This can be rewritten as 3 plus 417 over 10 to the third plus 417 over 10 to the sixth plus 417 over 10 to the ninth, etc. Now, we can write this as 3 plus the geometric series, n equals 1 to infinity, of the first term times 1 over, in this case is going to be 10 to the third, because we're going to add these exponents to get 10 to the sixth, and then add again to get to 10 to the ninth, etc. And here we'll have n minus 1. Again, pause the video, plug in 1 in for n, and verify that you get the first term, 417 over 10 to the third. Then plug in 2 and verify that you get 417 over 10 to the sixth, and then plug in 3, and so on and so forth. So again, we have a geometric series here, where in this case, a is 417 over 10 to the third, and r is equal to 1 over 10 to the third. And of course, absolute value of r is less than 1 again, so this series will converge to a, which is our 417 over 10 to the third, over 1 minus 1 over 10 to the third. This will give us 3 plus. If I multiply top and bottom by 10 to the third, I'll have 417 on top, and I'll have 10 to the third minus 1, which will give us 3 plus 417 over 1,000 minus 1 is 999. If we make a common denominator and combine these, we'll get 3,414 over 999. This reduces to 1,138 over 333. Example 3, find the value of x for which the series the sum n equals 1 to infinity of x to the n over 3 to the n converges. Find the sum of the series for those x values. So hopefully we recognize immediately that this looks a lot like a geometric series. So let's go ahead and write it in the format that we normally write our geometric series, a times r to the n minus 1. If you need to, pause the video and check that what we've written here is equivalent to this. Now, we have a equals x over 3 and r equals x over 3. In order for this series to be convergent, absolute r, which is absolute x over 3, has to be less than 1. Another way of writing that is that x over 3 has to be between -1 and 1. If we multiply both sides by 3, we'll get -3 less than x less than 3. So what this means is that this geometric series is going to converge only when x is between -3 and 3. We use the formula for a convergent geometric series, which is going to have a in the numerator, x over 3, over 1 minus the common ratio, like this. Multiplying top and bottom by 3, we get x over 3 minus x. So as you go ahead and do the rest of the problems on this worksheet, remember, every single problem will either be a geometric series, a telescoping series, or you'll be able to show that the series diverges using the test for divergence. Again, every single problem on this worksheet will be one of these three situations. So go ahead and do the rest of the worksheet.